Hello. I'm going to go through the OCR 2023, A Level Chemistry, Paper 1, Periodic Table, Elements and Physical Chemistry. If you find this video useful, please click like, and leave a comment, as it will help me to carry on making more videos like this. In the fixed comment under the video, I leave a link to my website jctnotes.com where you can see the written answers to this paper. In Section A, Question 1, we are given the masses of some hydrocarbons and asked which sample contains the greater number of molecules. To determine which sample contains the greatest number of molecules, we need to calculate the number of moles for each compound. The first step is to calculate the different molecular masses. The values that I get are 26 grams per mole for C2H2, 30 grams per mole for C2H6, 58 grams per mole for C4H10, 78 grams per mole for C6H6. If we divide the masses given for the molecular masses, I get 1.35 moles for C2H2, 1.50 moles for C2H6, 1.03 moles for C4H10, 1.28 moles for C6H6. The greatest number is 1.50, for C2H6, therefore the answer is B. In question 2, we have that 0.688 grams of an oxide of manganese is reduced by hydrogen gas to form manganese metal and 0.235 grams of water. We are asked to identify the formula of the oxide of manganese from the four provided. Writing the information provided helps to solve the problem. As each mole of water has 1 mole of atomic oxygen, 18 grams of water has 16 grams of atomic oxygen, then 0.235 grams of water has 0.209 grams of atomic oxygen. All the oxygen is provided by the oxide of manganese. We can calculate that the mass of manganese metal in the sample is the difference between the mass of the oxide and the oxygen from the water, giving 0.479 grams of manganese. The oxide metal can be determined using the same approach as calculating empirical formulas. In the description of this video, I have included a link with additional details on how to perform this calculation. I use a table with 5 columns. In the first column, I add the atoms. Oxygen and manganese in this case. In the second column, I put the atomic mass of each element. 16 and 54.9 respectively. In the third column I add the mass of each atom, 0.209 and 0.479. In the fourth column, the number of moles is calculated by dividing the mass by the atomic mass. I use several decimal places to minimize rounding errors. From these numbers, I choose the smaller number, and in the fifth column I divide each number of the fourth column by this number. In this case, the lowest number is 0.0872, and in the fifth column I get number of 1.5 for oxygen and 1 for manganese. Multiplying by 2 these numbers, we have the proportion oxygen-manganese is 3:2. Then, the formula is Mn2O3 and the answer is C. In question 3, we are asked how many hydrogen atoms are in 2.50 grams of pharmacolite. We are provided with the formula, the molecular mass and the 4 possible answers. Using the molecular mass and the mass given, we can find that we have 0.0116 moles of pharmacolite. As each mole has 5 moles of hydrogen, we have 0.058 moles of hydrogen. Multiplying by the Avogadro constant, I get 3.49 by 10 to the power of 22. Considering the rounding errors, the answer is D. In question 4, we have that 40 cubic centimeters of 0.2 mole per cubic decimeter of hydrochloric acid is added to 60 cubic centimeters of 0.1 mole per cubic decimeter of sodium hydroxide. We need to find out the concentration of the resulting solution from the four given answers. Using the concentrations and volumes given, we have 8 times 10 to the power of minus 3 moles of hydrochloric acid and 6 times 10 to the power of minus 3 sodium hydroxide. The reaction is 1 mole of hydrochloric acid reacts with 1 mole of sodium hydroxide to obtain 1 mole of sodium chloride and water. As we have more moles of acid, this is going to be in excess. After the reaction is completed, we are left with 2 by the 10 to the power of minus 3 moles of hydrochloric acid. All the sodium hydroxide has been consumed to produce 6 by the 10 to the power of minus 3 moles of sodium chloride. As the final volume, assuming that volumes are additives, we have 100 cubic centimeters or 0.1 cubic decimeters. Dividing the number of moles that we have by 0.1 cubic decimeter, the concentrations of hydrochloric acid is 2 times 10 by the power of minus 2 and the sodium chloride is 6 times 10 by the power of minus 2. This is answer C. Question 5 asks which of the four compounds shown has polar molecules. Hydrogen cyanide is a polar molecule because it has a linear structure, and there is a significant electronegativity difference between hydrogen, carbon, and nitrogen, creating a dipole moment. Boron trichloride is nonpolar despite the individual boron-chloride bonds being polar. The molecule's trigonal planar geometry makes the dipole moments cancel out. Carbon dioxide has polar bonds, but its linear structure causes the dipole moments to cancel out, making the molecule nonpolar. Tetrafluoroethylene is a planar molecule, where the dipole moments cancel each other. Therefore, the answer is A. Question 6 asks which of the given elements have the largest third ionization energy. The lithium in neutral state has 3 electrons. After removing 2 electrons, the third electron comes from the orbital 1s, which is very close to the nucleus. This orbital has a small radius, no other electrons shielding the nucleus charge, and it is strongly held. The other elements have more electrons that shield the third electron and larger atomic radius. Although energy is required to remove the third electron, in these cases, the energy is not as high as in the case of lithium. The answer is A. In question 7, we are provided with a reaction that is first order with respect to reactant X. When the initial concentration of X is 1 molar, the half-life is 16 minutes. We are asked what is the half-life when the initial concentration of X is 2 molar. Half-life is the time taken for the concentration of a reactant to fall to half of its original value. For a reaction that is first order with respect to the reactant, the half-life is constant and independent of the initial concentration. Then, the concentration at 2 molar is also 16 minutes. The answer is D. In question 8, we are asked which compound of the four provided requires the most energy to convert 1 mole into its gaseous ions. All the compounds listed are ionic solids. To break them into their gaseous ions, we need to overcome their lattice energies. The two key factors affecting lattice energy are ionic charges and ionic radii. The higher charges on the cation and anion result in stronger electrostatic attraction and therefore higher lattice energy. Smaller ions can pack closer together, increasing the strength of the attraction. Larger ionic radii reduce lattice energy. Since all the ions in the options are relatively small, the main factor here is the ionic charges. The sodium fluoride is formed by sodium +1 and fluorine -1. The sodium oxide is formed by sodium +1 and oxygen -2. The magnesium fluoride is formed by magnesium +2 and fluorine -1. The magnesium oxide is formed by magnesium +2 and oxygen -2. Magnesium oxide has the highest charges, giving it the strongest electrostatic attraction and the highest lattice energy. Therefore, magnesium oxide requires the most energy to convert 1 mole into gaseous ions. The answer is D. In question 9, we have the standard entropies of the sulfur dioxide, oxygen, and sulfur trioxide. We are asked to calculate the standard entropy change to form 1 mole of sulfur trioxide from sulfur dioxide and oxygen. In the case of a chemical reaction, we can calculate the standard entropy change by subtracting the entropy of the reactants to the entropy of the products. The formation of 1 mole of sulfur trioxide requires 1 mole of sulfur dioxide and half mole of oxygen. With the adjusted equation, we can calculate that the entropy is minus 254. The answer is B. Question 10 asks about the percentage dissociation of a 0.015 molar solution of methanoic acid with the dissociation constant provided. Based on the dissociation reaction, we have that we start with 0.015 moles of methanoic acid. We are going to dissociate X moles of methanoic acid and form X moles of protons and methanote anion. In equilibrium we are going to have 0.015 minus X moles of methanoic acid and X moles of protons and methanote anion. We can replace these values in the dissociation constant and obtain a quadratic equation. In weak acids, we can assume that X is much smaller than 0.015 and we simplify the equation and obtain that X is equals to 1.55 by 10 to the power of minus 3. The percentage of dissociation is the concentration of the dissociated acid divided by the initial concentration and multiply by 100. With these values, I get 10.3% and the answer is D. If you don't make the assumption that X is much smaller than 0.015 and work with the whole quadratic equation, you find that X is equals to 1.471 by 10 to the power of minus 3. This value gives a percentage of dissociation equals to 9.8%, the closest answer is given by D. In question 11, a student adds aqueous potassium carbonate to one test tube and aqueous silver nitrate to a second test tube. The student adds dilute hydrochloric acid to each test tube. Which row, of the 4 given, has the correct observations? We have a reaction in each test tube. In the test tube with potassium carbonate, this reacts with the hydrochloric acid to produce carbon dioxide gas, that will form bubbles and the student observes effervescence. In the other test tube, the aqueous silver nitrate reacts with the hydrochloric acid to produce a precipitate of silver chloride. The student observes a precipitate. Then, the answer is D. In question 12, we have electrode potentials of the half cells used in a lithium-ion cell and 4 statements. We are asked to identify the correct statement. For a reaction to occur spontaneously in a cell, the cell potential should be positive. To obtain a positive potential we invert the direction in the first semi-reaction and add it to the second. The potential of the cell is 4.20 volts, not 2.88 volts. A is not correct. At the positive electrode or cathode, the reduction reaction occurs, not the oxidation reaction given in option B. Then B is not correct. The overall reaction given in C is the one indicated. C is correct. The oxidation number of the cobalt in the cobalt dioxide is +4, each oxygen has an oxidation number of -2, and in the lithium cobalt oxide is +3, the lithium has an oxidation number of +1 and each oxygen has an oxidation number of -2. D is not correct. The answer is C. In question 13, we are asked which substance or substances have induced dipole-dipole interactions or London forces in the solid state, ethane, water, and silicon. Induced dipole-dipole interactions or London forces are weak attractions caused by temporary dipoles inducing similar dipoles in nearby molecules. Methane is a molecule that present London forces. In the water, the strongest intermolecular forces are hydrogen bond, but weaker London forces are still present. Silicon forms a giant covalent bond, therefore it does not present London forces. Then, the substances are 1 and 2 and the answer is B. In question 15, we have the molecular formula of a platinum complex and 3 different statements. We are asked which statement or statements are true. The molecule in question is cisplatin, which has a square planar structure. At the center of the complex is a platinum atom. 2 vertices of the square are occupied by chlorine atoms, while the other 2 vertices are occupied by ammonia molecules. This structure present bond angles of 90 degrees, therefore 1 is correct. The oxidation number of platinum is +2, as each chloride contributes -1 and ammonia is neutral. 2 is not correct. The molecule exhibits cis-trans isomerism, with ligands of the same type positioned either adjacent to or opposite each other. However, it lacks chiral atoms, so optical isomers are not possible. 3 is not correct. Only statement 1 is correct, and the answer is D. In question 15, we have the equilibrium of the decomposition of the chlorine trifluoride into its elements. We are asked which statement or statements of the 3 given are correct. The first statement asks if the reaction is a redox reaction. We have that the chlorine is reduced and the fluoride is oxidized. Statement 1 is correct. The second statement says that when the equilibrium mixture is cooled, the color fades. As the enthalpy of the reaction is positive, the reaction is endothermic. A reduction in temperature displaces the equilibrium to the left, fading the color. Statement 2 is correct. The third statement says that the decomposition has a negative entropy change. In the decomposition, we pass from 2 moles of gases, from chlorine fluoride, to 4 moles of gases, 1 from chlorine and 3 from fluorine, therefore the entropy increases and it is not negative. Statement 3 is incorrect. Only statements 1 and 2 are correct and the answer is B. We move to section B. Question 16 is about energy changes. Part A refers to calculation of lattice enthalpies using Born-Haber cycles. We are provided with a table of energy changes needed to determine the lattice enthalpy of barium iodide. In the first question we have an incomplete Born-Haber cycle to calculate the lattice enthalpy of barium iodide. We are asked to complete the diagram by adding the species present, including state symbols, on the dotted lines. Lattice enthalpy is the enthalpy change when 1 mole of an ionic compound is formed from its gaseous ions under standard conditions. In the case of barium iodide, we have 1 mole of barium-2 ions in gaseous reacts with 2 moles iodine ion in gaseous state to form 1 mole of barium iodide. This reaction is typically placed on the right-hand side of the cycle. I place it there. In the next step, I write the equations given in the question to help me to complete the cycle. I skip the verbal definitions to avoid making the video too long. Looking at the reactions, we can find that barium iodide is the product of the formation of barium iodide, then I fit the reactants in the cycle. I also write the value of the energy, as I will need it later on. Checking the next step up, we can see that we have changed the iodine solid to iodine gas. This is the atomization energy of iodine. This energy is defined by 1 mole of iodine and I have 2, I multiply the energy by 2. Going up in the cycle, we have barium solid. The only reaction that we have with barium solid is the atomization of barium. We complete the next dotted line with the barium gas and the iodide gas. I also add the energy. Going up in the cycle, we can see that in the next two steps we are going to remove 2 electrons from the barium. The iodine does not change. The first step is the first ionization energy of the barium. The second step is the second ionization energy of the barium. We have completed the first question. For completeness, as I will need on the next question, I add the first electron affinity of the iodine. Careful, as it is defined by 1 mole of iodine gas and we have 2, I need to multiply by 2 this energy. In the second question, we are asked to calculate the lattice enthalpy of barium iodide. Hess's law tells us that the overall energy change of a chemical reaction remains the same, no matter the pathway or sequence of steps taken, as long as the initial and final states are identical. Therefore, the reaction between solid barium and solid iodine to form solid barium iodide releases -602 kilojoules per mole. This energy change will be the same whether the reaction happens directly, marked with the arrow in yellow, or through an alternative route, such as forming barium 2 plus gas and iodine -1 ions before they combine, arrows marked in orange. Replacing the values that we have, we can get a lattice enthalpy of -1872 kilojoules per mole. In part B of question 16, we are given the first and second ionization energies of magnesium and strontium. We are asked to explain why the first ionization energy of magnesium is greater than the first ionization energy of strontium and to explain why the second ionization energy of strontium is greater than the first ionization energy of strontium. Ionization energy is the amount of energy required to remove 1 mole of electrons from 1 mole of gaseous atoms or ions to form positively charged ions. In the case of magnesium, the first ionization energy is magnesium gas to produce an ion of magnesium +1 and 1 electron. Therefore, ionization energy is related to the strength of the attraction between an electron and the nucleus of an atom or ion. In the first question, explain why the first ionization energy of magnesium is greater than the first ionization energy of strontium. The reason is that magnesium has smaller atomic size and reduced shielding result in a stronger nuclear attraction to the outermost electron, making it harder to remove. In the second question, why the second ionization energy of strontium is greater than the first ionization energy of strontium, the reason is that after the first electron is removed, the remaining electrons experience a stronger effective nuclear charge and are closer to the nucleus, requiring more energy to remove. In question 17, we are given the reaction of production of bromine. A student investigates the rate of this reaction by carrying out 4 experiments at the same temperature and we are provided with the results. We are asked to explain how the reaction orders can be determined from the student's results, and determine the rate equation and rate constant for this reaction. To measure reaction rates, we change the concentration of one reactant while keeping the others constant. The rate equation for this reaction can be expressed as the product of the constant, K, by the initial concentrations of each reactant to the power of their respective reaction orders. By comparing experiment 1 and experiment 2, we see that in experiment 2, the student has trebled the concentration of bromine, while keeping constant the other reactants. The initial rate also trebles, which suggests that the reaction rate is directly proportional to bromine. This means the reaction order with respect to bromine is 1. We can use or using a more systematic approach, if we replace the data given for experiment 1 and experiment 2 in the rate equation and divide the expression obtained by experiment 2 by the expression obtained for experiment 1 and simplify, we get that 3 equals 3 to the power of A, then A equals 1. If we compare experiment 1 with experiment 3, we notice that in experiment 3, the initial concentration of bromine has been doubled, while the concentration of bromate has been halved. Despite these changes, the initial rate of reaction remains the same. Since we already know that the reaction order with respect to bromide is 1, A equals 1, we can conclude that the reaction order for bromated is also 1, B equals 1. Alternatively, we can divide the expression of the rate equation of experiment 3 by experiment 1 with the value of A equals 1. Simplifying, I get 0.5 equals to 0.5 to the power of B, then B equals to 1. The only reaction order left is C. The initial concentration of protons has only changed in experiment 4. At this stage, I found easier to use the rate of equation with the information that we have, including that A and B are both 1. Dividing the expressions obtained for experiment 3 and experiment 4 and simplifying, I get 0.04 equals to 0.2 to the power of C. Taking logarithms, I get that C equals 2. We can replace the reaction orders in the equation rate. The reaction constant can be calculated by using the data from any of the experiments. Taking experiment 1, I get a value of K equals 16.4. To finish the exercise, we need to calculate the units of K. We use the rate equation, making K the subject and replacing the relevant units. We get moles to the power of -3 times decimeters to the power of 9 times seconds to the power of -1. With this, we have the value of K and the rate equation. Question 18 is about enthalpy changes of reactions involving hydrocarbons. In Part A, a student determines the enthalpy change of combustion of heptane by heating 150 grams of water with a spirit burner containing heptane. The temperature of water increased by 10.5 degrees Celsius and the mass of heptane used is 0.133 grams. Using these results, we are asked to determine the enthalpy change of combustion of heptane, in kilojoules per mole. The temperature increase in the experiment is due to the heat released during the combustion of heptane. Assuming there are no heat losses, the heat energy can be calculated by multiplying the mass of water by its specific heat capacity from the data sheet of the exam and by the increase in temperature. In kilojoules, this number is 6.5835. But this number refers to 0.133 grams of heptane. Using the molecular mass of the heptane of 100 grams per mole, we can find that the enthalpy change of combustion of heptane is -4,950 kilojoules per mole. Be careful with the sign. Enthalpy of combustion is an exothermic reaction. In fact, we are using it to heat the water, therefore the sign should be negative. In Part B of question 18, we are provided with the breakdown of nonane by heat to form pentane and ethene and its enthalpy change. We are also provided with the enthalpy changes of combustion of pentane and ethene. We are asked to determine the enthalpy change of combustion of pentene by using the enthalpy change of the provided reaction and the enthalpy changes of combustion in the table. To solve the problem, we can use that the enthalpy change of the reaction is the difference between the enthalpy changes of combustion of the reactants and the enthalpy changes of combustion of the products. Using this equation, we have that the enthalpy change of the reaction is the enthalpy change of combustion of nonane minus the addition of the enthalpy change of combustion of pentane and 2 times the enthalpy change of combustion of ethene. Note that as in the reaction we have 2 moles of ethene, I need to multiply by 2 its enthalpy. Replacing the values that I have in the problem and making as subject the enthalpy change of combustion of pentane, I get that its value is -3,535 kilojoules per mole. Alternatively, we can use Hess's law. Hess's law states that the total enthalpy change of a chemical reaction is independent of the path taken, as long as the initial and final states remain the same. We have that the decomposition reaction requires 186 kilojoules per mole. We also know that the combustion of nonane to produce carbon dioxide and water is minus 6,171 kilojoules per mole. We have the combustion of the ethene is minus 1,411 kilojoules per mole. If we use 2 moles, we need to double the quantity to minus 2,822. We finally have that the combustion of the pentane is going to have a value that we call X. As per Hess's law, the total enthalpy of the direct combustion of the nonane is the same that the energy required to decompose the nonane in pentane and ethane and combust both of them. This means that minus 6,171 is equals to 186 plus X minus 2,822. Making X the subject, we have that X is equals to minus 3,535 kilojoules per mole, the same as using the formula. In question 18c, we have the reaction for the production of ethene produced from ethanol, where ethanol in the gaseous state is converted into ethene and water, both in the gaseous state. In the first question, we are asked to predict the sign of the entropy change for the reaction, explaining our reasoning. The sign of the entropy change for reaction 2 is expected to be positive. This is because entropy is a measure of disorder or randomness in a system. In the reaction, the number of gas molecules increases during the reaction, going from 1 molecule of ethanol to 2 molecules, ethene and water. This increase in the number of gas particles results in a greater distribution of energy and higher randomness in the system, leading to an overall increase in entropy. In the second question of part 18c, we continue with the same reaction for the production of ethene produced from ethanol. We are given the Gibbs equation with the statement that the enthalpy change and the entropy change can be assumed to be constant at different temperatures. We are provided with a graph showing values of the free energy change at different temperatures for the given reaction. Using the graph, we are asked to draw the best fit line on the graph, determine the increase in entropy on joules per Kelvin and mole, determine the minimum temperature at which the reaction is feasible, and determine the enthalpy change. To ensure the best fit, use a ruler to draw a straight line that aligns as closely as possible with all the data points. Since the values derived from this line will be used in the rest of the exercise, it's important to extend the line as far as possible, preferably until it intersects with the graph's axis. The increase of entropy represents the slope of the line just drawn. To determine it accurately, select values that are spaced as far apart as possible. In this case, I chose points where the line intersects the axis. For the increase of Gibbs free energy I have 45 minus 60 equals to 105. For the temperature, I have 830. The division gives me 0.127 kilojoules per Kelvin and mole. As the answer is required in joules per Kelvin and mole, I multiply by 1000 and get 127 joules per Kelvin and mole. The minimum temperature at which the reaction is feasible is when Gibbs free energy becomes negative. Using the line in the graph, we see that it is 0 when the temperature is 350 Kelvin, or similar values, depending on your graph. At higher temperatures, Gibbs free energy is negative, then the answer is 350 Kelvin. The enthalpy change is the y-intercept. When T equals 0, the value of enthalpy change is equals to 45 kilojoules per mole. Question 19 is about oxides of nitrogen. In part A, we are given an equilibrium. In the first question, we have a sealed flask containing 6 moles of nitrogen dioxide heated to a constant temperature and allowed to reach equilibrium. The equilibrium mixture contains 5.4 moles of nitrogen dioxide and the total pressure is 5 atmospheres. We are asked to determine the value of Kp, giving the answer to 3 significant figures. we need to include an expression for Kp and its units. The expression of Kp is the partial pressure of N2O4 divided by the square of the partial pressure of NO2. As the partial pressures are given in atmospheres, the units are atmospheres to the power of -1. We need to find the partial pressures of the N2O4 and the NO2 in equilibrium. These can be found by multiplying the total pressure by the molar fraction of each element. To find each molar fraction, we need to figure out the number of moles in equilibrium of NO2 and N2O4. We do it by using an initial, change and equilibrium, table of the components of the reaction and filling with the data that we have. Initially we have 6 moles of NO2 and none of N2O4. In equilibrium, we have 5.4 moles of NO2. We know that for each mole of N2O4 formed, we have lost 2 moles of NO2. Let's call x to the number of moles of N2O4 formed, then, we have lost 2x moles of NO2, i.e. 2x. In equilibrium, we have the addition of the initial and the change. This means that in case of the NO2, 5.4 is equals to 6 minus 2 times x, and in the case of N2O4 is x plus 0. Solving the equation for the NO2, we get that x equals to 0.3. We can complete the table and find that the concentration in equilibrium of N2O4 is 0.3. The total number of moles in equilibrium is 5.7. With these values, we can calculate the partial pressure of the NO2 as 4.737 atmospheres, and for the N2O4 we have 0.263 atmospheres. Replacing these values in the value expression of Kp, I get 1.17 by 10 to the power of -2, using two significant figures. In the second question of Pad 19a, we have that the sealed flask in the last question is then heated to a higher temperature at an increased pressure. The system is allowed to reach equilibrium again. We are asked to explain why it is difficult to predict how these changes in reaction conditions affect the amount of N2O4 formed at equilibrium. As the reaction is exothermic, the enthalpy is negative, according to Le Chatelier's principle. Increasing the temperature favors the reverse reaction. Consequently, this shift reduces the amount of N2O4 formed at equilibrium. On the other hand, increasing the pressure favors the direction with fewer gas molecules. In this equilibrium system, the forward reaction reduces the total number of gaseous molecules from 2 moles of gas to 1. Hence, higher pressure shifts the equilibrium to the right, increasing the yield of N2O4. These two opposing factors, increasing temperature favoring the reverse reaction and increasing pressure favoring the forward reaction, make it difficult to predict the overall effect on the amount of N2O4 formed at equilibrium. In question 19b, we have that N2O4 reacts fully with oxygen to form a different oxide of nitrogen, oxide A, as the only product. We know that oxide A is collected and cooled to 75 degrees Celsius at a pressure of 101 kilopascals. Under these conditions, oxide A is a gas that occupies a volume of 74 cubic centimeters and has a mass of 0.28 grams. We are asked to calculate the molar mass of oxide A and suggest its molecular formula. To determine the number of moles of the oxide A, we use the ideal gas equation. Remember to use the right units for each variable. I get that we have 2.58 by 10 to the power of -3 moles. Dividing the mass of the oxide by this number of moles, I get a molar mass of 108 grams per mole. Now, it is question to play around with the atomic masses of nitrogen and oxygen to find that the combination that gives a molar mass of 108. This is N2O5. Any other combination of nitrogen and oxygen will not get closer. Question 20 is about acid and bases. In Part A, we have a table with the ionic product of water at 25 and 40 degrees Celsius. In the first question we are asked to calculate the pH of water at 40 degrees Celsius, giving the answer to 2 decimal places. The ionic product of water is the product of the molar concentration of protons and hydroxyl ions. In pure water, the concentration of both are the same, then the ionic product of water is the square of the concentration of protons. Replacing the values that we have, we get that the concentration of protons is 1.7088 by 10 to the power of -7. By definition, the pH is the negative logarithm of the proton concentration. We can calculate that the pH, to 2 decimal places, is 6.77. In the second question of this part, a student make the statement that the water is neutral at the given temperatures in the table. We are asked to explain why the student is correct. The answer is because in pure water, the concentration of protons and hydroxyl ions is the same. In part B of question 20, a student reacts strontium metal with water to make a 250 cubic centimeters solution of aqueous strontium hydroxide. The solution contains 0.145 grams of strontium hydroxide. We are asked to write an equation for the reaction of strontium with water and to calculate the pH of this 250 cubic centimeters solution of strontium hydroxide at 40 degrees Celsius, referring to table 20.1 and giving the answer to 2 decimal places. The reaction of strontium with water produces strontium hydroxide and hydrogen. The molecular mass of strontium hydroxide is 121.6 grams per mole. 0.145 grams of strontium hydroxide is 1.1924 by 10 to the power of -3 moles. Dividing this number by the volume of the solution, we have that the molar concentration of sodium hydroxide is 4.7696 by 10 to the power of -3. It is a strong base, completely dissociating in water, and each mole of strontium hydroxide produces 2 moles of hydroxyl ions. Then, the concentration of hydroxyl ions 9.5392 by 10 to the power of -3. Using the value of the ionic product of water from table 20.1 and this concentration of hydroxyl ions, we get that the concentration of protons is 3.061 by 10 to the power of -12. The pH is the negative logarithm of this value. Rounded to 2 decimal places, the pH is 11.51. In part C of question 20, a student reacts 1 gram of strontium carbonate with an excess of dilute nitric acid. A gas is produced. In the first question, we are asked to construct the equation for this reaction. Strontium carbonate reacts with dilute nitric acid to produce strontium nitrate, carbon dioxide gas, and water. In the second question, the student reacts 1 gram of calcium carbonate with an excess of dilute nitric acid. We are asked to explain why the student's 2 reactions produce different volumes of gas. The molar mass of strontium carbonate is greater than that of calcium carbonate. Since the same mass, 1 gram, is used, fewer moles of strontium carbonate will react compared to calcium carbonate, producing less moles of carbon dioxide. In part D of question 20, a student reacts an excess of magnesium with 25 cubic centimeters of 0.5 molar hydrochloric acid. The student also reacts an excess of magnesium with 25 cubic centimeters of 0.5 molar ethanoic acid. In the first question, we are asked to construct an ionic equation for the reaction of magnesium with an acid. The magnesium displaces hydrogen ions from the acid, releasing hydrogen gas. Remember that we are asked by the ionic equation, not the full molecular equation. In the second question, we are asked to explain why these 2 reactions of magnesium produce the same volume of gas but at different rates. Exam tip: since this part of the question is worth 3 marks, the examiner is likely looking for three distinct points. Bullet points help to identify key ideas, helping to score full marks. The reaction rates differ due to strength of the acid. Hydrochloric acid is a strong acid and completely dissociates in solution, instantly providing a higher concentration of proton ions. Ethanoic acid is a weak acid and only partially dissociates, releasing protons gradually. Proton concentration and collision frequency. The higher initial concentration of protons in hydrochloric acid results in more frequent collisions with magnesium atoms, leading to a faster reaction rate. Ethanoic acid has a lower initial proton concentration, slowing down the reaction. Final number of protons. Over time, more ethanoic acid molecules dissociate to release enough protons to match those provided by hydrochloric acid. This ensures that both reactions produce the same volume of gas by the end. Part E of question 20 refers to butanoic acid, a weak monobasic acid. In the first question, we need to explain what is a monobasic acid. This indicates that 1 mole of acid donates 1 mole of protons. Be sure to specify that this applies per molecule or mole of the acid, as failing to clarify this point could result in losing marks. In the second question, a buffer solution is prepared by dissolving 3.39 grams of potassium hydroxide in 250 cubic centimeters of 0.376 molar butanoic acid. This buffer solution has a pH of 5.07 at 25 degrees Celsius. We are asked to calculate the acid dissociation constant of butanoic acid at 25 degrees Celsius, assuming that the volume of the solution remains constant at 250 cubic centimeters when the potassium hydroxide is dissolved. To simplify, I use AH instead of butanoic acid and A- instead of butanoic ion. To obtain the value of the dissociation constant, we need to find the concentrations in equilibrium of the protons, butanoic acid, and its ion. The concentration of protons can be found from the pH. Since the pH is 5.07, the concentration of protons is 10 to the power of minus 5.07, giving a value of 8.51 by 10 to the power of minus 6. The butanoic ions come from the potassium hydroxide reacting with the butanoic acid. As the acid is a weak acid and the potassium hydroxide is a strong base, we can assume that all the potassium hydroxide is neutralized by the acid. The moles of potassium hydroxide can be calculated by dividing the mass 3.39 grams used by its molar mass of 56.9 grams per mole, giving an result of 0.0604 moles of potassium hydroxide. Since each potassium hydroxide molecule produces one butanoate ion, the number of moles of this ion in the buffer is also 0.0604 mole. Dividing this value by the volume of 0.25 cubic decimeters, we get the concentration of 0.242 molar. To calculate the concentration in equilibrium of butanoic acid, we start by calculating the initial number of moles given by the 250 cubic centimeters of 0.376 molar, that gives a value of 0.094 moles. But 0.0604 of these moles had reacted with potassium hydroxide to form A-, then in equilibrium, we have 0.0336 moles of butanoic acid. If we divide this number but the volume of 0.25 cubic decimeters, we have a concentration of 0.134 molar. Replacing these values in the formula of the acid dissociation constant, we get a value of 1.53 times 10 to the power of minus 5. Part F of question 20 asks to explain why the pH of buffer solution with pH 4.5 does not change when a small volume of water is added. The pH stays the same because the ratio between the concentrations of the weak acid, Ha, and its conjugate base, A-, doesn't change. In a buffer solution, this balance is what maintains the pH. Adding water dilutes everything equally, so the proportions of Ha and A- remain consistent, and the pH doesn't budge. Question 21 is about grass fertilizers contain compounds of iron washed into a nearby river causing the water to be polluted with a mixture of iron 2 and iron 3 ions. In Part A, a student determines the concentration of iron 2 ions in a sample of river water by titration with potassium manganate 7. The student uses 25 cubic centimeters portions of river water by acidifying with dilute sulfuric acid. Each portion is titrated with 0.0025 molar potassium manganate 7 until a color change is seen. We are provided with the equation of the titration reaction. There are 3 questions in this section. In the first question, we are asked to state the color change seen at the end point of the titration. This was definitely a bit of a tricky question, as many students get caught out by mixing up the color change or providing incorrect colors. Check out a link that I leave in the description for the colors of inorganic ions and complexes for A Level Chemistry from OCR, very helpful for OCR exams. The color change is from colorless to pink, or pale purple. The mark scheme accepts pale purple as an answer, but not just purple. This happens because all the iron 2 ions have reacted, leaving a tiny excess of potassium manganate 7, which gives that light pink tint. The potassium manganate 7 is originally purple, but when diluted, it can appear lighter in color. In the second question, we are given the student's titration results, omitting the trial titer. We are asked to complete the table and calculate the mean titer that the student should use to determine the concentration of iron 2 ions in the river water. The titer volumes for each titration is obtained by subtracting the initial volume from the final volume. This gives 12.65 for the first, 12.95 for the second and 12.75 for the third. Now, titers need to be concordant. That means you only use values that are close together, within 0.10 cubic centimeters of each other. In this case, titers 1 and 3 are concordant, so you ignore titer 2 when calculating the mean. The mean of titer 1 and 3 gives you a value of 12.70 cubic centimeters. In the third question, we are asked to determine the molar concentration of iron 2 ions in the river water. We start by finding the moles of manganese 7 used in the titration by multiplying the volume used in the titer and its concentration. This gives 3.175 times 10 to the power of minus 5 moles. To calculate the number of moles of iron 2, we check that from the stoichiometry of the reaction, each mole of manganese 7 reacts with 5 moles of iron 2, then, the student has titrated 0.5875 times to the power minus 4 moles of iron 2. The molar concentration of iron 2 is given by dividing the number of moles by the volume of the portion in cubic decimeters. This gives a value of 6.35 times to the power of negative 3. In Part B of question 21, the student modifies the experiment in Part A to determine the combined concentration of iron 2 and iron 3 ions in the river water. The method has 3 steps. In step 1, the student adds an excess zinc to a 250 cubic centimeters sample of river water and warm gently. In step 2, the student cools the solution and remove excess zinc by filtration. In step 3, the student acidify with 25 cubic centimeters portions of the filtrate from step 2. Then titrate each portion with 0.00250 molar potassium manganate 7 until a color change is seen. We are given a table with 3 redox systems. We are asked to use the information in the table to explain the reasons for step 1 and step 2. We need to pay attention to the possible reactions happening within the system. Remember that a more positive potential value favors the forward reaction. Step 1, adding zinc and warming gently. Zinc is a reducing agent, and it's used to convert all the iron 3 ions in the river water sample into iron 2 ions. This process works because zinc has a more negative standard electrode potential. Step 2, filtration to remove excess zinc. After step 1, there is still leftover zinc metal that needs to be removed, otherwise it will react with the potassium manganate 7 during titration because the zinc has a more negative standard electrode potential. Question 22 is about the D block elements in period 4 of the periodic table, scandium to zirconium. In part A, we are asked to explain, with examples from period 4, what is meant by the terms D block element and transition element and why some D block elements are not transition elements, using electron configurations to support the explanations. A D block element is one whose highest energy or valence electrons are found in the D subshell. In other words, the d orbitals are being filled with electrons. For example, iron has the electron configuration of argon, 4s2, 3d6, so it is a d block element because its d subshell contains electrons. A transition element is a special kind of d block element. It forms ions with an incomplete d subshell. For example, iron 2 ions have the configuration argon, 3d6. The D subshell isn't full, which makes iron a transition element. Not all D block elements fit the definition of a transition element because they don't form ions with a partially filled D subshell. For example, scandium and zinc. Scandium forms scandium 3 ions, which have the electron configuration argon. The 3D subshell is empty, so scandium isn't a transition element. Zinc forms zinc 2 ions, which have the electron configuration argon, 3d10. The 3d subshell is completely full, so zinc also isn't a transition element. Part B of question 22 has 2 questions. In the first question, we are asked to describe precipitation reactions using either copper or chromium ions as examples, including equations. I will give the answer for both options, but you only need to give one. When copper 2 ions react with sodium hydroxide or ammonia, copper 2 hydroxide forms as a pale blue precipitate. Note that an excess of ammonia will dissolve the precipitate, forming a deep blue solution, as we will see in question 2 of this part. When chromium 3 ions react with sodium hydroxide or ammonia, chromium 3 hydroxide is formed as a dark gray-green precipitate. Note that an excess of ammonia or sodium hydroxide will dissolve the precipitate, as we will see in question 2 of this part. In the second question, we are asked to describe ligand substitution reactions using either copper or chromium ions as examples, including equations. I will also give the answer for both options, but you only need to give one. Copper 2 aqua ions have 6 molecules of water as ligands. It can undergo ligand exchange with chloride ions or excess of ammonia molecules, resulting in distinct color transformations. In the reaction with ammonia, 4 water molecules are replaced by 4 molecules of ammonia, changing the color from pale blue to deep blue. In the reaction with chloride ions, we have the formation of a complex with 4 chloride ions, changing the color from blue to yellow, while the final color might appear as green due to the mixture of blue and yellow colors. In this reaction, we also have the change of structure of the complex, as chloride ions are larger than water and ammonia. Chromium 3 aqua ions also have 6 molecules of water as ligands. They can undergo substitution reactions with excess hydroxide or ammonia. In the reaction with excess of ammonia, all the molecules of water are replaced by ammonia and the color change from violet or pale purple to purple. In the reaction with hydroxide ions, the 6 water molecules are replaced by 6 hydroxide ions, changing the color from violet or pale purple to dark green. In part C of question 22, we have that the ethane diode ion is a bidentate ligand. A complex ion of cobalt-3 contains 2 ethane diode ligands and 2 water ligands. We are asked to determine the charge of this complex ion and the coordination number of cobalt in the complex ion. We start with the charge. The cobalt-3 has a +3 charge. Each ethane diode ligand has a 2 negative charge. As we have 2 of these ligands, the total contribution is -4. The water ligands are neutral, adding no charge. The total charge of the complex is 3 - 4 + 0 = -1. Thus, the charge of the complex ion is -1. Now, we move to the coordination number. Ethane diode is a bidentate ligand, meaning each molecule forms 2 bonds with cobalt. As we have 2 of these, their total contribution is 4 bonds. 2 water ligands contribute 2 more bonds. The total number of bonds to cobalt is 4 + 2 = 6, meaning the coordination number of cobalt is 6. In part D of question 22, we have that an acidified solution containing dichromate ions reacts with vanadium-3 ions in a redox reaction to form a solution containing chromium-3 ions and vanadium ions. We are asked to construct the overall equation for this reaction. We have a redox reaction with all the species provided. As it is in acidic solution, we might need to use protons. I use half equations. We start by identifying the elements that are reduced and oxidized. In the oxidation, we have that the vanadium-3 oxidized to vanadium. In the reduction, the dichromate is reduced to chromium-3. In the next step, we write their half reaction balancing the elements except for the hydrogen and the oxygen. We only need to add 2 to the chromium-3 in the reduction. In the third step, we balance the oxygen atoms by adding the appropriate number of water molecules to the opposite side of the equation. This is done by adding 2 molecules of water as reactant in the oxidation reaction and 7 as the product in reduction. In the fourth step, we balance the hydrogen atoms, including those added in the previous step, by adding protons to the opposite side of the equation. In the oxidation, we add 4 protons as products and in the reduction 14 as reactants. In the fifth step, we add up the charges on each side and add electrons to equalize the charges in both sides of each half equation. In the oxidation reaction, we need to add 2 electrons to the products and in the reduction 6 electrons to the reactants. Then, we compare the number of electrons in each half equation and made them equal by multiplying with convenient numbers. In this case, we multiply the oxidation by 3 to obtain 6 electrons in each half reaction. Now, we add both half equations, followed by cancelling the electrons and any common terms in reactants and in products. We can cancel the 6 electrons on each side. We remove 6 molecules of water on both sides, leaving 1 as product. We finally cancel 12 protons on both sides, leaving 2 as reactants. Then, the answer is 3 vanadium-3 ions react with 1 dichromate ion and 2 protons to produce 3 vanadium ions, 2 chromate-3 ions and 1 molecule of water. And this is the end of the paper. If you want to see more videos like this, please click like, and leave a comment, as it will help me to carry on making more videos.